I said I wanted to go over each chapter and give you an idea of what to focus on in each chapter. All the readings will come right out of here, Essentials of Facial Growth, 2nd edition. And today, we're going to go over chapter 14, which is on bone and cartilage. The learning objectives, which are in the blackboard handouts, are to know the physiologic, i.e. functional differences between bone and cartilage. So let's start with that, the functional differences between bone and cartilage. Bone and cartilage are structural tissues for the human body. And if we think of bone as a hard tissue like this, and cartilage as the shock absorber like that. So generally, we don't have bones contacting other bones. We always have in between the shock absorber. So the functional significance of bone is rigid support. The functional significance of cartilage is shock absorbing. So if we look at the way the skeleton is put together here with my friend, all the joints will be lined with cartilage. So at the end of all the long bones, you're going to have a cartilage cap. Why? Because you're going to be exerting force there. And bone itself cannot resist pressure. We're going to talk about why that is. Why can't bone resist pressure, but why can cartilage? Why is cartilage the shock absorber? Why is bone just there for rigid support? Let's look at the structure of these tissues. Go over to the board here. I'm going to talk about the simplest situation, which is just a long bone. So we take a long bone, such as the humerus here. And in the growing person, each one of these bones is actually 3 bones. There's what we call the epiphysis, the diaphysis, and another epiphysis. So each long bone in a growing individual is actually 3 bones. In between the diaphysis and the epiphysis is the epiphyseal growth cartilage. So we've got growth cartilage here in the long bones between the epiphysis and the diaphysis. Now, very important, covering all of this is a membrane which we call periosteum. So periosteum covers all of the bones in the body. So if you look at the skeleton here, every place you have a bone, you've got a covering of periosteum. What's in the periosteum? Well, in the periosteum, we have the cells that create new bone, called osteoblasts. We have capillaries, and we have the nervous innervation. So we've got innervation, capillaries, and osteoblasts all in this covering here. It's a thin covering, it's soft tissue, and therefore if you press or exert pressure on the periosteum, you compress the capillaries and you cut off the blood flow. So if you put pressure on periosteum, what happens is you end up causing bony resorption. Bone cannot grow under a pressure situation. So that's why we need cartilage. So we see cartilage here in terms of growth cartilage. We also see cartilage on the ends of all the articular surfaces here. So here we see what we call hyaline or articular cartilage. Whereas here, we have growth cartilage. So you see, cartilage occupies a unique position within the appendicular skeleton, and we'll see also within the face. But it's much simpler to understand in the appendicular skeleton, in that growth cartilages are responsible for creating tissue separating force to allow the long bones to grow. So we need to resist the forces of gravity, so we need to be able to push bones apart, and cartilage in the terms of the epiphyseal growth plates is able to grow and actually push bones apart. Then that cartilage is converted into new bone. So long bones grow in length by the process of endochondral bone formation. So you get growth at the epiphyseal plates, which displaces the epiphysis from the diaphysis. That cartilage is then converted to bone. We call that endochondral bone formation. And we get increases in the length of the bone. Increases in bone width are totally different. Nothing to do with the growth cartilage. So I'm going to erase this right now. I just want you to kind of capture that in your mind. We're going to go on to the next point, which is how do long bones grow in width? In width, we'll now take that long bone that I had, and we're going to cut it in cross section. Now we're looking at that long bone, but we'll cut it in cross section. So we, just like this bone here, if I cut it right in the center, and then we turn it, we're going to look at the end of the bone. So we're looking down the shaft. Remember, we have periosteum covering the outside of the bone. And on the inside of the long bone, we have what we call endosteum. So inside, you have the endosteum. On the outside, you have the periosteum. Endo meaning inside, peri meaning the periphery or on the outside. So these soft tissue coverings over the bone contain on both periosteum and endosteum the osteoblasts, innervation, blood supply, and the way a bone grows in width is by the deposition or the addition of bone at the free periosteal surface. So what we see in growth of bones in width is the addition of new layers of bone here, with the periosteum always staying on the outside. So we get this bony deposition. And in order to keep the bones from getting too heavy, on the endosteal side, we'll often see endosteal resorption. So we'll see on the endosteal side where we actually get the resorption of bone and an increase in the marrow space. So to summarize, the bones grow in length by endochondral bone formation, and they grow in width by deposition on the periosteal side and resorption on the endosteal side. So I wanted to go and look at our learning objectives again just to make sure we're covering everything. So the physiologic differences between bone, we talked about bone and cartilage being pressure resistant, bone being tension adapted. And we're going to talk about, well, why is cartilage able to resist that, the pressure of gravity, the articular pressure when we chew. So what's unique about cartilage compared to bone? We talked about bone having that thin, soft tissue covering of periosteum that has the capillaries and the osteoblasts and the nervous innervation. And of course, compression or pressure put on the periosteum is going to compress those capillaries. Why doesn't that happen in cartilage? Well, if we look at the structure of cartilage, and there are several different types of cartilages, and you'll learn that in histology. But if we look in general now at drawing the end of the bone again, and now we're drawing that cartilage cap, that articular cartilage there. Why is articular cartilage able to withstand pressure? Well, it's very simple. Articular cartilage, first of all, has a lot of fibrous tissue and a lot of water, and we can get diffusion of nutrients through the cartilage because it's not ossified. So here, in an articular cartilage, if we were going to look now at cell bodies, we'd see that we have a lot of amorphous ground substance and very few cell bodies. In fact, hyaline, the word means cell-free. So cartilage can exist, first of all, without any soft tissue covering. So cartilage can exist without a perichondrium. It could exist with the perichondrium or without a perichondrium. In the articular cartilage, it doesn't have a perichondrium because the pressure of the articulation would just squeeze out the capillaries. We'd have the same situation we have in bone. So cartilage is able to resist the forces of gravity because it is cell-free, high in water content, that nutrients can diffuse to nourish the few cells, the few chondrocytes that we do have within the articular cartilage. So it's very springy and very spongy. So that's the reason why cartilage is able to resist pressure. We talked about the two different ways bone is formed, endochondral and intramembranous. Intramembranous directly from fibrous aggregation of fibroblasts. Know the difference between deposition and resorption. Well, we talked a little bit about deposition. Deposition is very simply the addition of new bone at a free surface. So, looking again at our cross section of the long bone, remember we had the endosteal surface and the periosteal surface. So we got the endosteum, and it has what? Endosteum on the endosteal surface, periosteum on the periosteal surface. Deposition means the addition of new bone. Addition of new bone, deposition. It is what we call a surface activity. So it's a bone surface activity. Bone can only grow on surfaces. So deposition is the addition of new bone. We could have addition of new bone occurring on the outside or the periosteal side. We call that then periosteal deposition, addition on the outside. We could also see addition of bone on the endosteal side. What do you think we might call that? Well, endosteal deposition. When we see dissolution of bone on the surface, like you see here, now we're removing bone, we call that resorption. And if it occurs on the outside, we can call it periosteal resorption. If it occurs on the inside, like you see here, I showed this before, where you might see bone being dissolved here, what do you think we'd call that? Endosteal resorption. So we talked about deposition and resorption, the addition of or subtraction of bone from surfaces. If it occurs on the outside, we term it periosteal. If it occurs inside the bone, it's endosteal. The last learning objective that we haven't talked about is the biological importance of cutting and filling cones. So for this, I want you to think about this for a minute. If bone, once it's formed, all of the osteocytes are encased in hard material. So all of the osteocytes are encased inside the bone. They have to be fed by little capillary systems. And so you've got this living cell inside the ossified bone. So the question becomes, if that osteocyte, which is a mature cell, certainly it can't divide. Well, it can't divide because it's encased in its lacunae. If it divided, it would kill itself from the pressure. So bone can only grow on the surfaces. It's not capable of growing interstitially. So what happens when we've got this bone and we have a cell that dies within the bone? What's going to happen? How are we going to replace that dead cell? Or if we get injury and it injures osteocytes inside of the bone, how are we going to replace them? That's where the cutting and filling cone comes in. So let me just show you what that looks like. And there's more of this in the book, and I would hope you would review this because it's difficult to draw it totally accurately on the board here. But remember that within a bone, we've got the osteocytes, and then connecting all the osteocytes, we have the little capillary network, and then we have all the bony trabeculae. So each osteocyte is encased in bone. It's in a little bone prison. When that cell dies, how are we going to get in there and replace that? Well, the cutting and filling cone is like a rotor-rooter for bone. It's a very small structure. You'll see it diagrammed in the book. But think about it like this. It's a tubular structure. And on the end, on the very end, it has osteoclasts. So the very end of it is osteoclasts, which are capable of resorbing bone. And then on the inside, we've got the osteoblasts. So we're laying down new bone. So we're resorbing bone, and then we can lay down new bone. So we can resorb the dead bone and lay down new bone. What it looks like when a cutting and filling cone has been through filling cone cuts through and replaces the old bone with new bone, it looks like a target. So we see these targets, they're called osteomes. We see them all the way through mature bone. And they're there for two reasons. They're there because we have bony repair that needs to be done, and they're also there because it's important that the skeleton is the reservoir for calcium in order to keep the calcium level constant in our bloodstream. Remember the calcium gates that allow nutrients to go in and out of cells. So our body calcium concentration is regulated at a very fine level, and that's done by using bone as the calcium reservoir. So the older you are, the more you see these secondary osteomes, the more the cutting and filling cones have had to go through the bone, and they go there in order to get calcium for the bloodstream and also during the repair process. Also important for you to look at in the book is the fact that cutting and filling cones are responsible for the osseointegration of titanium implants that we use in dentistry. So there's a lot to review in this section on bone and cartilage, chapter 14. Again, we're just going to run down the learning objectives, know the physiologic, i.e. functional differences between bone and cartilage, understand the physiologic significance of cartilage in weight-bearing areas, such as the humerus, know 2 different ways bone is formed, know the difference between deposition and resorption, be able to describe how a long bone, such as the humerus, grows in length and width, and know the biological importance, and I would add the dental importance, of cutting and filling cones. So I hope this helps you approach Chapter 14 in a responsible and prepared way. And there's a lot of information in there, and it's the kind of information that you'll be able to use throughout your dental career. Thanks.